Um, Good afternoon. Welcome to yet another webinar by Roman Bells AV from Sweden. My name is Lorraine, and I will be your host for the next 30 minutes. Today, we present to you an introduction about pressure process regulators. But before we start, here is some practicalities. First of all, let us know immediately if you do not see the slide moving to the next slide. The next thing is there will be uh, questions and answers at the end of the presentation. So please feel free to write any questions as we go along in the chat. Then we will address that at the end of the webinar. Good. So let's start. So the agenda for today is I'm going to make a quick company presentation about Raman, discuss what is a pressure regulator, how it compares with a control valve, the types of process regulators, the principle of operation, typical applications, basic regulator rules, question and answers. I'm also going to just quickly show you our product platform. So Raman was founded in 1945 with the headquarters in Bromma, Stockholm. We have our own manufacturing site in Fagersta, Sweden, about 12 employees, and a worldwide distribution network. Our products and services includes control valve, process regulators, safety valve, tank safety equipment, automation accessories, consultation, sizing and selection, and service and maintenance. We have our own brand, the Raman ball sector valve, ball sector control valves. We also represent several companies in the Scandinavian and Swedish market, which is Rose, Badgermeter, Control Air, Unival, and Casco. Today we're going to focus on Casco's pressure reducing valves, but let's get to Casco. Who is Casco? Casco is a company about 100 years old with their headquarters in USA, Kansas. It has also a European manufacturing facility in Copenhagen in Germany. Casco's product portfolio consists of control valves, linear and rotary, industrial regulators, back pressure and pressure reducing regulators with different configurations, pilot operated, pressure loaded, etc. Then Casco has a full range of tank blanketing, pressure relief valve vents, emergency vents, gauge hatches, and flame arresters. So what is a regulator? A regulator is a self-contained, mechanical, spring-operated or pilot-operated device used to maintain a desired set pressure within a system. It functions independent and does not rely on any external input. So depending on the function, it can be categorized into the following types: pressure reducing regulators and back pressure regulators or pressure sustaining regulators, and then differential pressure regulators. So a pressure reducing regulator in this situation, the picture on the screen, use the force balance principle to reduce and maintain the downstream pressure in the pipe. In this example, the upstream pressure is reduced as it passes through the regulator. When the process requires more flow, the pressure under the diaphragm will decrease and allow the valve to open more, while maintaining a constant downstream pressure. This balance force ensures a steady downstream pressure. Now, how does it differ from control valves? A control valve loop or control loop where a control valve is employed will need typically a pressure transmitter if it's pressure control. And that pressure transmitter then gives a feedback to a controller, PLC, DCS system. And this controller then gives a feedback to the positioner or the I2P for the valve. The valve then gets a signal from that positioner to the actuator, and it opens and closes the valve more or less. Usually these systems are PNID controllers, and the loop just repeat as the pressure varies in the system. Well, a regulator consists of an adjusting knob, a spring, which could be tensioned by the adjusting knob, a diaphragm, where the pressure is exerted by the spring force. And by adjusting the adjusting knob, you adjust the P2 pressure. If you want to change the pressure, you physically have to come to the regulator and then make any changes. All right, let's get to types of regulators. Now, again, pressure regulators are a throttling device that varies the plug or seat opening to maintain a constant pressure upstream or downstream of the regulator. So a pressure reducing regulator is where we control the P2 pressure. Back pressure regulators is where we control or sustain the inlet pressure to a specific set point. Then we have differential pressure regulators. Differential pressure regulators is a proportional only control device that maintain a constant differential pressure between a reference pressure and the pressure of the controlled fluid. So if we quickly look at this graph here, the bottom graph is the loading pressure, which is loaded inside the diaphragm area of the regulator. Then we have a spring. In this case, it is set at 2 bar. The loading pressure is set at 10 bar. And these two will allow us to get to a P2 pressure of 12 bar. Let's assume the inlet pressure is 20 bar. So as the loading fluid changes, the pressure changes in the loading fluid, the P2 pressure will follow that set point the whole time. Good principle of operation. So regulators, how does regulators work? Regulators work on the force balance principle that has been mentioned a few times now. So in the pressure P2 built downstream, if the pressure P2 built downstream, the regulator closes slightly to decrease the pressure. If the pressure P2 decreases downstream, the regulator opens to build pressure. So the P2 is smaller than P1. This regulator have a little spring at the bottom of the plug, and that is one force that we need to calculate for. Then we have the forces of the inlet pressure below the plug. We also have the force of the P2 pressure on the bottom of the diaphragm area. And this forces equals the force from the spring on the top of the diaphragm plus the force of the P2 pressure on the plug. So the force upwards equals the sum of the force downwards. Now regulators operate with proportional band only, and this gives us what we call a droop or a bolt curve. So the amount of variation in controlled pressure with a given flow, with a given change in flow is called a droop. So in this case, let's assume that we have one valve open and a steady flow, and we set the pressure at a specific set point. As the process requires more flow, the pressure below the diaphragm will decrease, and the regulator will take in a new position with the spring not being adjusted at all. And this will cause a decrease in pressure where it actually will control. And that can be for a droop curve, could be 10, 20, 30, 40%. The bolt curve where we control P1 pressure is the same principle. As we set the pressure at the one fixed set point and the flow increases, the set point actually increase of the regulator because nobody physically go to the regulator and adjust it. It is still having the same spring at the set at the original set point, and that will control the pressure with an offset. In this case, let's assume 30%. So how to increase the accuracy of pressure regulators? Because the built-in droop curve is the function of the spring inside the regulator. So one, you can use a larger body, which means higher capacity, higher CV or KV value. Use a composition diaphragm. A composition or soft diaphragm have the ability to flex more than a metal diaphragm, which is fixed. Use the largest port size. Again, it's about capacity. It will give you more accuracy. Eliminate the device that's creating proportional effect. The device that's creating the proportional effect is the spring. By taking it away, making a dome-loaded regulator, a pressure-loaded regulator, or a pilot-operated regulator might increase the accuracy. So for overlapping spring ranges, use the softer range spring. You will sometimes see that, for instance, 35 psi setting, use a 10 to 40 range spring rather than a 30 to 80 psi range spring. The softer range spring will give you more travel, which will increase the accuracy of your regulator. Then add reset to your proportional regulator. That's possible, but that's a whole topic on its own. Then add a longer spring range, exhibit less droop. A longer spring range exhibit less droop. So, and if you can incorporate this into several of these ideas into your regulator, then you can decrease the amount of variation in your segment when there is flow changes or higher demand for flow. The configuration. So we have several type of regulators, and I'm also going to just touch on one of them, but I'm not going to in detail in that. Basically, we have mechanical regulators and electronic regulators. Mechanical regulators, spring-loaded regulators, and dome-loaded regulators. Dome-loaded regulators can then be either be pressure-loaded, or the next slide will show you pilot-operated. Then also we have electronic regulators. Electronic regulator is a regulator that are being calibrated by getting, unfortunately, an external signal, but it's a fixed signal, and it will control then the regulator. Let's say it's calibrated for 4 to 20 milliamps to 0 to 10 bar, and then you can adjust it where you want the set point to be. Then we have mechanical pilot operated regulator. We have a spring-loaded pilot. There's this pilot, and there's a spring in the pilot, and it's getting the sensing on the pilot. The sensing is not happening on the main valve. Then we have a dome-loaded or pressure-loaded pilot regulators. Again, this is even more accurate than the spring-loaded regulator, and you will get almost 0% deviation from set point as the flow demand changes. Then there's another option is you can have electronic pilot on top of this dome-loaded regulators and control your point to which this could also be a closed loop system. So now we're going to discuss a few applications. For today, I'm going to discuss cryogenic storage tanks for cryogenic pressure reducing valves, cryogenic back pressure regulators, and customer use pressure reducing valves. I'm also going to discuss a pump recirculating valve or pump relief regulator, as it is known for. I'm also going to discuss a compressor seal pressure control system for differential pressure regulators. Just a quick thing, this is not just the only applications, there is many to think about. You can control the temperature of the system by controlling the steam pressure, because it's much easier and much quicker to change the temperature if you do control the steam pressure, because they are related to each other. We have oxy fuel burners, which we can use control of your mixture of your gas, your natural gas or your oxygen. There's many to think about. Good, but now let's get to the cryogenic storage tank. So a cryogenic storage tank is which you will usually see at facilities that's using nitrogen, oxygen, and these are huge tanks, vertical tanks standing next to a system where you get an ambient air vaporizer, and the liquid is then vaporized and being used as gas downstream to the client. So in this case, when the tank is being filled with liquid, the liquid we will have no gas at the top. The liquid is going through this regulator, and this regulator is called the pressure built regulator. the pressure belt regulator can be either on the liquid side, which is cryogenic temperatures, or it can be on the gas side. It will still be cryogenic feature, but it will just be a different size of regulator because gas expanded. So this pressure belt regulator will build the pressure through this system and increase the pressure of the vapor on top. As the pressure increases, this cycle will just continue until it reaches, let's say, 12 bar, if that is the set point of the pressure belt regulator. This is a small vaporizer, ambient air vaporizer, that will vaporize the controlled pressure P2 to a gas on the side. In the event that the tank heat, for instance, and this increases, and not to vent it to atmosphere and lose the use of this gas could be vented by what we call a economizer regulator, and it's nothing else than a back pressure regulator. The back pressure regulator or the economizer regulator then vents the gas into the customer supply line, which will then be able to be used. This is a typical Casco model BQ. This is a typical Casco model D or 1000 HP. There is other situations where we can use a differential pressure regulator and control this pressure in this tank within 2 psi of set point. Then as the gas, let's go on, as the gas go to the customer use, it's being vaporized by ambient air vaporizer and turn into gas and then go to the client. So the pressure on the inlet side, because of the pressure in the tank being controlled by the pressure belt circuit, is at 12 bar. The client only use 5 bar, so we need to control this pressure with, in this case, is called DA4 or the SLR or the ULR regulators, and it's being controlled at a specific set point to the customer use. Many times the customers have wide range abilities, and that is why we will have a dome-loaded regulator for better accuracy. This is typical soft diaphragm, soft seat, and pilot operated or pressure loaded. Good. Then we have back pressure regulators. So I'm going to take the diagram on the right. So we have a pump that supplies several printing presses. That is many years ago. But this is also called a ring main. The best way to control the pressure in a ring main is to control the back pressure at the end of the line, and not to control the pressure by reducing the pressure. As we control the inlet pressure to the back pressure regulator, we're controlling the pressure to all the printing pressures at the same set point. As the one printing press goes out of service, or maybe more gets into service, it keeps on controlling the pressure, say at 100 psi in this situation. We have both 3-port and 2-port back pressure regulators. So in this case, we have P1 the same on port 1 and 2, and the port 3 is our relieving port back to the tank. Now, I'm going to discuss with you a differential pressure regulator. Now, differential pressure regulator, the sketch might be look very complicated, but it's not. This is a compressor with a seal, mechanical seal there. This is our seal oil. This is the reservoir for the oil and the pumps to supply the seal oil to the compressor. And this is the gas in the compressor supplying the client use, intake and outlet. So let's just discuss the outlet for interesting. So as the compressor pressure increases the gas side, it also increases the pressure on the top of the diaphragm. And because this has been set to a physical set point to keep a specific differential pressure across the seal, as the pressure in the diaphragm increases, it increases the pressure of our seal oil so that it's always, let's for instance say 2 bar across the mechanical seal. The same goes for the low pressure side. as the gas of the intake increases, it will increase or control the oil across the seal oil, the seal of the seal oil on the seal. This is typical application. So just to quickly read here, spring in the differential pressure regulator maintain lubrication or seal media on the rotating equipment. The differential is maintained relatively to internally sensed turbine or compressor pressures. Good. We have several rules when it gets to regulators. And rule number one is pressure regulators regulate pressure. They do not regulate flow. So it's important to select a regulator for the proper flow rate. Rule number two, flow rate and control pressure are integral. If the flow changes, a change will occur in the controlled pressure. This is the droop and build curve, which we discussed already. Rule number three, there is the use of composition, soft diaphragms, will provide maximum flow, minimum droop or build, and better accuracy. Rule number four, process regulators do not fail in the most frequent desire mode most of the time. Rule number five, regulators are best used in systems where flow changes are small. Although our DA series has a 2000 to 1 rangeability. Do not rely, rule number six, do not rely on regulators as shut-off devices. And when you shut off, preferably shut off the pressure before a regulator and not downstream of a regulator. That will save your regulator. Never hydrostatic test pressure regulators. And last, rule number eight, reducing regulators nearly in all cases have two separate pressures versus temperature ratings, one for the inlet and one for the outlet. Good. So now it quickly takes me to our product platform. This is where you can find regulators and quickly find maybe the one that you want. So if we select on ramanvalves.com, we go to products, and to products, we can select process regulators. Process regulators then takes you to a configurator. The configurator, then you can select whatever valve or regulator you want to configure, and it will take you to a selection process. Now I'm going to regulator website, and I'm just going to put it here and just share the screen. Not sure if that, let's just do that. Okay, maybe it's not going to work. Let's see if this is working. Okay. Excuse me, I just want to, I'm not going to be able to find that. Let me just go back. So again, I just want to say, so from the website, we go to regulators. From the regulator, you can go to the configurator. And from the configurator, you can select the detail about the regulator, what you want to do. Unfortunately, I'm in a webinar and I cannot share more detail at this stage. So, any questions? Let me see in the chat. I don't see anything. Lena, do you see any questions here?
No, no questions.
I can quickly, I see no questions, so I can try. I see we've still got some 5 minutes left. I can quickly try to share the product platform, and I think that would be very useful to a lot of people. I'm going to try my best to do that. Share window, this one. Okay. I want to know if, Lena, you can just give me feedback. Am I sharing the product platform?
Yes.
Okay, good. So just to quickly show you, so I went to Raman valves, I went to products, and I select pressure reducing regulators. And for instance, I know what I want. I want a Model D pressure reducing regulator, and I want to configure it. So I go to the configuration. Okay. We just wait for a signal here. And then I will make it a little bigger so everybody can see. It is the Model D. On the left, we just see this is the general. So it's from a 3/8 inch to a 1/8 to a 1 inch. So Model D, PT, extended nipples, and it's for the water industry, gas industry. So in this case, we want an oxygen regulator, 3/4 inch, a DN20, and we want to set it at 5 bar, so we can select a 5.5 bar. We also can select the 4.8 to 10 bar, but we've just learned that a better accuracy regulator would be to have the lighter spring, and that's why we select that one. It's configured that the oxygen will only take the B4. Bronze is good. We have different materials. We have stainless steel available. We have carbon steel available. In all our regulators, we have most of all materials available. On the left side, you will be able to see some specifications about the regulator. You will get some detail in this, and you can change the language into Swedish, and then you will have everything in Swedish, but mine will stay in English. Then after you've done that, you have data sheets on the bottom here, and you add to cart, or you can compare the two regulators with each other. So that is my presentation for the day. I hope it was useful, helpful, and Alina, I'm not sure if there's any questions yet. You can just let me know.
There's just one question about the presentation, and we will share it afterwards. Yes.
Okay. Thank you very much. Good. I think then this is what we have. Thank you very much for joining us in this webinar. Please don't hesitate to email us. Please don't hesitate to send us your inquiries. We can do a proper sizing and selection. As I said again, we have several types of regulators, several type of sizes, up to 4-inch, different materials, different spring ranges, up to 208 bar. So whatever you have in your system, please let us know. We will try to assist you. Thank you very much.